get started? It's about time, I guess. Welcome, everyone, to another CAN seminar series presentation. Today is September 17th, and we are having our first outside speaker for this semester's CAN seminar series. And with us, actually, we have Professor Amlan Mukherjee from Department of Civil and Environmental Engineering, Michigan Technological University, Michigan Tech. And Professor Mukherjee, Amlan, is an associate professor in the department at Michigan Tech, and he's also the founder of Life Cycle Solutions, LLC. So his PhD is from University of Washington, Seattle. He was telling me that his co-advisor was Professor Joe Mahoney, some of us very familiar with, know him well. And also his research and teaching and all the entrepreneurial efforts have focused on integrating life cycle thinking into design, construction, and maintenance of civil infrastructure systems. So Amlan serves on Federal Highways Sustainable Pavement Technology Working Group. He's also a specialty editor of ASCE's Journal of Construction Engineering and Management, and is currently serving on the ASCE's Digital Project Delivery Committee. So with that, I would like to welcome him to ATRL, to University of Illinois, and he's going to talk about pavement smoothness over time, and how roughness issues deal with estimating pavement life cycle use phase emissions. He'll be giving us examples from the LTPP database. So,
thank you very much. Can you hear me at the back? Okay, yeah. Thank you very much. I really appreciate the invitation. It's been a pleasure visiting this morning, and I'm looking forward to the rest of the afternoon too. I'm going to be first and foremost, I do apologize because the title up there is not quite the title that I sent ahead of time, but it's really the same talk. It's just slightly different angles. But I guess what brings me here is that in the last few years we've been looking at pavement sustainability. There's been a lot of work and a lot of, and of course, Dr. Al-Qadi is very involved in much of the work, and I've been part of the TWG, which has to a large extent also driven and influenced my research. So I have a background in construction, but a lot of what I've been doing is looking at large construction data and how that construction data can be modeled and used for different kind of decision-making problems. And so in the last 7 to 8 years, I have kind of gravitated towards applying or understanding how these databases can be used for life cycle assessment. And I've been working with life cycle assessment of pavements, and increasingly, I think, and much of our conversations this morning, quite a few conversations this morning, we're talking about, well, when it comes to life cycle assessment, there are many different problems that make up life cycle assessment is a fairly big problem. And there are many different problems. There are some of us working on UHI, there's PVI, there's questions of performance. And a lot of these models, a lot of these questions, we address them through mechanistic models and then lab tests. And then there is also increasingly a wealth of empirical data. And so the questions are, and some of the empirical data is very necessary when we get down to doing life cycle assessment and understanding the systems that we're modeling. So the question is, how do we tie some of these data, these large bodies of empirical data, even before we tie them into the theory? Well, where do we get them from? How do we organize them? How do we analyze them? And at the end of the day, who are the ones who are going to be using these data sets for decision-making purposes, and how do we empower the decision makers, right? So within that context, I'll be talking about the pavement vehicle interaction problem, right? Which and this is my starting motivation slide. I've been using this motivation slide for the last 7 years now, and I've realized that it's still fairly relevant, right? We want to reduce greenhouse gas emissions. That's the big problem, and that relates to the general challenges of climate change. And in order to do that, we have developed strategies, and some of the strategies are operational and some of them are strategic. So operational strategies, right down to on a construction site, reducing cycle times and making your operations more efficient. And we've done some work on that to show how more efficient construction operation planning helps reduce your emissions better construction in the long run reduces maintenance needs. There's all of that. And then strategically, well, there is alternative designs, and there's a lot of work happening in that, use of recycled materials, but also improved decision processes. And so what I tend to focus on is the strategic aspects of improved decision making, and then tying it down to some of the specific problems in life cycle assessment and see how we can do it better. I think I have something here. Oops. There we go. Okay, so one of the what I'll be talking about today is that we do know that building and maintaining smoother pavements is a good idea, and intuitively that's because smoother pavements reduce your fuel consumption over. And personally, for you on your vehicle, you may not notice a major difference, but given the entire fleet, that the numbers add up very quickly. And so, of course, there is the added benefit that it's a much pleasanter experience driving on a smoother pavement. So the question is, how do we, what do we know about pavement roughness, and how does that relate to fuel consumption? Okay? And how do we tie that into some of our life cycle assessment work, right? So, so why smoother pavements? All of that, and then we want to reduce rolling resistance, and then NCHRP 720, and there's been quite a bit of work and quite a bit of work coming out of this university too, which shows that roughness is definitely a significant factor. Pavement roughness is a significant factor. Pavement deflection, there are all these other areas where energy is being lost at that pavement vehicle interface, but roughness is definitely one of the most significant factors, right? So the other, so given that roughness is a significant factor, we know the IRI measure is used, the International Roughness Index is used to measure roughness, right? And all states don't use it, but most states are using it at this point, and Federal Highways is pushing for IRI to be used. It's used in inches per mile or meters per kilometer. And then one of the best part of it is that it's generally speaking an objective quantity, an objective measured quantity, and is reproducible. And so this is the part where I have to put in a caveat, is that usually when I give a version of this talk, afterwards somebody comes and says, I don't think you understand. We really don't know how to measure IRI. And my response to that is, I hope you're working on it, because I don't care. What I'm working on is the stuff that you're producing. So we tend to work with IRI data, and we tend to draw our conclusions from IRI data. So if the IRI data is not perfect, some of those imperfections will show up in our studies, and we recognize that. So we recognize that as a limitation. And but I mean, I think in the generally speaking, we know that it's a reliable metric, and partly also because a lot of the IRI data is being used to to calibrate and validate various existing systems, and so we look at it as not as if it's because of these inefficiencies in measurement. We don't look at it as if it's an inherent absolute value, but more as an approximation for the pavement, and say, well, if there are trends in this, the trends may not, so you have the reality, you have the trends, and the trends may reflect the reality, but we're not suggesting that this is exact measurement, more of an estimate. So what the IRI measure does, despite its imperfections, is that it helps you come up with good estimations. And so when we're looking at greenhouse gas emissions during the use phase, it's a useful metric to use to measure, to estimate these emissions, right? So in the context of use phase emissions, well, we want to minimize pavement use phase emissions, because we've seen in various studies, and this numbers come through in quite a few studies, including some of our previous studies, that 80 to 90% of the life cycle emissions are happening during the use phase. So that's after a pavement has been commissioned, post-construction, right? And then with respect to IRI, we know that a change in 2 meters per kilometer gives you a 1 to 2% reduction in fuel consumption, right? Which, again, strictly speaking, is not a very big difference on your personal vehicle, but within the fleet that translates into quite a significant difference. So the challenge is how to estimate these use phase emissions, assuming and understanding that that this is fundamentally a dynamic value we're looking at, because traffic changes over time, your pavement condition is deteriorating over time, and so we have to consider this as a time-dependent process. Okay, so given that it's a time-dependent process, how do you associate and estimate these use phase emissions? So the question really is, how does fuel consumption change over time as the pavement deteriorates? So not just how does fuel consumption change with IRI, but you have to kind of look at that in the context of how does it change over time as the pavement is deteriorating, right? when what we wanted to do was first and foremost answer questions of like, first question is how does the IRI change over time? Because we use the IRI change over time as approximation for pavement deterioration, which we're using to look at roughness. And then and also understand what are the conditions that influence the IRI. So are there relationships with pavement type? Are there certain trends we can see with pavement type? Regional factors, are we seeing these trends come up differently because of climatic differences? And traffic loading. So what are the factors that are driving the relationship of IRI change over time? And also, strictly speaking, based on the data, if we can get the empirical data, what kind of maintenance plans help us deliver smoother pavements, right? So the fundamental question we're looking at is how does fuel consumption change over time, right? So we can write that as a simple differential rate of change of fuel consumption over time, and we can reduce that down to this simple product, which is rate of change of fuel consumption as a function of roughness and multiplied by rate of change of roughness over time, right? And so when you do that, we find that the first part of the problem we have a good handle on because we understand how fuel consumption changes with respect to IRI, okay? So, and how do we know that? This is out of Dr. Kiran Chetty's work at Michigan State, right? And this table has been used in various other works to look at use phase emissions, where we have an idea that for a given vehicle class, for different speeds, starting with a base IRI of 1, how your IRI changes. As your IRI changes, what percentage does your fuel consumption change by, right? So, for example, if you're starting at for a medium car with base IRI of 1, as you go from IRI 1 meter per kilometer to 2 meter per kilometer, you have a change of 3% to 5% and so on in that particular table. So, and of course, this also plays out for different speeds, which, as we know, the different speeds do make a difference. So, and that's the basic assumption that I should have gone to that earlier. So now, so essentially, what we have these are fuel consumption with respect to change of IRI and their adjustment factors, right? So starting with a base of 1, how do they change? So really, this part of the problem, we can reduce it down, and those are the plots that you get out of that table. It's a straight line plot for different vehicle classes for different speeds, right? And really, if you take that, so you reduce it down to that simple equation, it's a straight line equation. So at 70 miles per hour, for example, what your fuel consumption is going to be as your IRI changes, okay? So starting off that y is equal to 1 at IRI equals to 1 meter per kilometer. So that's an adjustment factor. So that's useful that we already have that model in place. Right? So the next question that we want to look at is how does IRI change over time? So what is the relationship between IRI and time? And so this is where the lessons from the LTPP data come in, is that, so can we go back and look at what empirical data we have and what can we learn from the empirical data, okay? So our goal was, well, let's analyze the LTPP sections. And the reason we used LTPP is not because LTPP is the best data set for this, but more that this is a very publicly available data set that we can work with. And then some of the critiques that we've gotten on this work is that, well, why are you using LTPP for this? Because a lot of the LTPP data was for various different purposes, and I'll address that in a second. But in the grand scheme of things, one of the goals of this work is that we start off with LTPP, but we're right now trying to say that if you have IRI data, whether you're a state agency or a county, if you have good IRI data and you're wondering how to best manage your resources, we can still apply these methods within the system that we've built to give you the trends that you need. So that's the general goal, right? But the way we do that is we start off with the LTPP data, we start off by understanding it more of the national level. Can we cross-classify the data by region, traffic load, different kind of pavement types? And so for the presentation, we present a lot of our results in terms of asphalt, jointed plane, and continuously reinforced, because that's where we're seeing the major differences in trends. But really, if you start playing with all the different combinations of bases and so on and so forth, you find that there are actually really 17 pavement types. And so we really like to see it within that broader spectrum. Time of day measurements. In this particular study, we haven't quite gotten to the part where we're looking at time of day measurements, but in the long run, I think we want to start looking at that because it could throw some light on curling and how does that affect. So, well, the first thing we did was we took all the LTPP data and just threw it out there on a plot, and this is what it looked like. So clearly there are plenty of challenges with working with LTPP data, and if you have, and most of you probably have looked at it, is that there are, you have to clean the data fairly well before you can even start using it. So we said, well, why don't we start off with a data set that's already been used for some purpose, so and assume on the validity of that data set and build from there. So we started off with looking at what we call the pre-validated data set, was the IRI data set that was used to calibrate the MEPDG IRI change models. So we're like, well, if that's been used, there's definitely some validity to it, and so let's start off with that, and then see what differences we get as we apply the same test to the larger body of data, right? So we started working with that data set, subset, and part of the reason is, again, that for that particular subset, the model IRI calculations closely correlated with the observed IRI calculations from the LTPP database. So this was a subset where the IRI measure, as I'd spoken previously, that there were concerns about the reliability of the IRI measure. This was a subset where that reliability, this was a fairly reliable data set to work with. Again. And then, of course, all results that I'm going to be reporting are at level of confidence 95% for hypothesis testing. So, right. So some of the complicating factors, as I was mentioning earlier, is that the LTPP data set got about 20 years, early 90s data sets from then. So there are some sections that are very well documented in terms of the maintenance that has happened. There are other sections that are not as well documented, and it's probably because they rolled into the program at some point later on, or they fell off the program at some point. For some reason or the other, there are places where there are clearly you see changes in IRI with no maintenance or construction having been done to it. So we had to go through a cleaning process to actually take some of those sections out. The other concern is that the LTPP database has all the different studies, and each study was, the pavements for the studies were done for various different reasons. The reason why the sections are there in the database were often to measure other issues, but the IRI was also measured for it. So that is a concern, but as I mentioned earlier, if the IRI was measured, well, the IRI was measured, and IRI is IRI. So there might be some confounding factors because there might have been special case sections put in. And so the response to that is that, well, generally speaking, we're not suggesting that you take this as the gospel truth, but look at it as, given a large data set, what can we do with it? And then take the conversation to the next step is that, well, what other large data sets do we have with this kind of infrastructure data that we can then start filling in and use the same thing, okay? The LTPP data can sometimes be difficult to access. For us as academics, it's not necessarily as difficult to access, but people who would be making use of some of this data for decision making, they oftentimes find it difficult to access. So we kind of kept that in mind, and it's going to come up later on in my presentation on how we think the need to create accessibility to these data sources is critical. The other thing is, the other thing is that oftentimes when we speak about these large data sets, we tend to use the word or use to model the data, using assumptions of a normal distribution. And when we get into the data a little bit, you realize that that's a problematic thing to do, because a lot of this data, it tends to follow failure statistics a lot more than it does any kind of more central behavior. So potentially useful factors. So what was the metric? We decided to come up with one clean metric that we could use to understand this rate of change. And again, there are issues that different states have different kinds of policies. And once a pavement has gone, post-construction, once you get into, well, depending on what funds were available, what your maintenance schedules were, you're bringing in all sorts of confounding factors, right? So to minimize those confounding factors, we said, well, let's look at the initial IRI starting from the point at which the section got into the database or new construction, and the final IRI at the time of first intervention, right? So initial IRI and final IRI at the time of first intervention, assuming that at the point they were coming in, they were in similar conditions, right? And then what was the time to intervention? So initial IRI, the IRI at the point of first intervention, and the time to intervention. So using those three numbers, we thought we could identify the factors that affect the change of IRI over time. So you're looking at initial time to first intervention and the IRI at the point of intervention, right? And so the question was like, let's look at the region, climate, pavement type, traffic loading, throw all these numbers out there and see what we get, right? So again, as I pointed out, that this is a fairly noisy database, okay? And so what we were looking for is that are there any trends that we find coming out irrespective of the data subset that we're using to analyze, whether it's or the question that we're asking of the data. So the one general trend that came through across all these different all the different subsets as well as all the different questions that we're asking is that asphalt, the AC pavements tend to have a lower initial IRI, but has a faster degradation rate, right? And so if you look at by region, we're seeing seeing the similar pattern in pretty much every region. There are parts of North Central where it gets a little, it goes the other way, but those sections we later on trace back to having very specific problems. So generally speaking, this was, and then also from that you could understand what the first intervention years were, right? So typically in the southern region, you're going between southern and north central, interestingly, you're going between 15 to 16 years, whereas in the North Atlantic and western region, you're looking at 10.8 to 11.8 years, right? And we also did, we looked at it by region, but then we also flipped it and looked at freeze thaw behavior, and you're finding that those wet freeze, the dry freeze, and the completely dry regions, and you find that those regions actually fall out pretty well along those numbers too. So you're finding, generally speaking, between 15 to 16 in some regions and between 10 and 11 in other regions. So then trends by base type is that you find that both of them, with asphalt pavements, you're seeing a lower initial IRI for treated bases than for untreated bases, and this is not unexpected. Concrete pavements, even though we hear that there is, in DOTs are looking at using more stabilized bases, we're finding that in terms of the data that we have, we didn't find any major sensitivity there. Effective interventions, we looked at, of course, and then some of these are expected, that you're finding these major reduction in IRI between 20 to 30% for joint repairs, slab replacement, surface grinding, and also different kinds of surface treatments. They reduce your IRI by 20 to 40%. Now, what are the sequences that work best? Again, we're getting into a situation where the data is not probably the best to answer that question, right? So the general lessons from analysis, again, when you look at it through the many different subsets that we analyze, and I'm not getting into all the details out here, is that the one common signal that comes across is, generally speaking, the asphalt pavements tend to have a lower initial IRI, but in the long run, their rate of change is greater than, is steeper than for concrete pavements, right? So again, we use mostly failure statistics to handle some of the stuff, and this is all within the 95% confidence interval, right? So generally speaking, if you just classify all the pavements, you get a range. So you find the CRCP slope, which is the green one, is a flatter slope, and they tend to give you there are some sections that give you extremely smooth behavior and with little or no degradation for a period of 20 years. Now, of course, construction, how the pavement gets constructed has a lot to do with that, and that's, again, information we don't have, right? But this general slopes between the AC and the jointed plane, you're finding those slopes coming out to be pretty consistent, and doesn't, again, despite the noisiness of the data, it doesn't matter which subset you're using, you're finding that trend coming quite clearly, right? So going back to the PVI question here is that, so now what we have is based on these trends out here is we can do an IRI over time curve, right? So IRI as a function of time, given that at t equals t naught, you have the initial IRI and the rate of change of IRI k. And that rate of change actually turned out to be quite linear. It was, we were wondering if linear models would be good, but based on the data, the linear models were not a bad fit. Okay. So now, so if you combine those two, right? So now you have a relationship for fuel consumption over time, right? And so based on, so using Chatty's work with fuel consumption over IRI and multiplying it by the relationships we got with IRI over time, what we could do is we could now start looking at fuel consumption change over time, right? So this goes back to the question of, so when we're looking at pavement smoothness, and we're trying to understand the impact of pavement smoothness or roughness on fuel consumption, we have to start. It's not a well, it's very useful to know what the percentages are as IRI changes, but we also have to look at what do those trends look like as the IRI changes over time, right? So if you have two different pavement types, and so one that has one starts with a slightly higher IRI and finishes at a higher IRI, but has a slightly lower IRI change rate, compared to another pavement that has that starts at a lower IRI and has probably, well, in this case, two more interventions over the same period of time. What you do is your fuel consumption change over time, so it becomes the area under that curve, right? So on the x-axis you have, sorry, on the y-axis you have the fuel consumption percentage change, and on the x-axis you have time. And so the idea is that when you're looking at fuel consumption with respect to time, you're looking at that curve rather than just the specific factor. So now, of course, one of the things that you learn from the data is that because of the wide variety in data, it would probably be it would not be a very good, even though we're seeing this one trend about the rate of change of IRI, it would probably not be a good idea or maybe we should be very careful on how we generalize some of these trends across large databases, as well as across or how we convert that into practice and say, well, this is how we should be looking at for pavement type selection. So the idea is that how do you take the data that we have for a given network and use and consider network-based approaches that helps decision makers answer similar questions using the similar underlying methods to and using their own data to be able to make decisions, right? So what we did was we started off building this with the LTPP data again because it provides us a nice system to work with. But right now we're in the process of integrating other data sets for IRI, especially data sets that were actually measured with IRI and IRI-based actions in mind, right? And so the goal is to create transparency for these data sets and allow customized assessment by the stakeholders. So if you're a DOT administrator, decision maker, and you're looking at prioritizing your pavement maintenance, and smoothness typically is part of that decision. So you can start looking at your network-wide data and also understand where some of the variations in that network-wide data come along. Because when analyzing the LTPP data, there are sections which don't typically tend to behave how you would have expected them to behave, and oftentimes we don't understand or don't have all the details of what went on with that section, and sometimes it's lack of data, or sometimes it's the fact that we don't know some peculiarity of the context in which that section was built. As a project manager or as a decision maker within an agency, you have the ability to understand some of that and say, well, that behavior is happening because it could be traced back to a funding decision at some point, right? So what we did was we took all of this stuff and we put it in a database. And so right now this is this iraexplorer.com. You can access this website, and we've been having, I think some of you have used it, we've been having people use this. One of the things that we're finding is that, of course, the data set is not perfect, and that's true. But then we've also had some people come to us with data sets that they have that they can put in and use it for their own purposes. So in the long run, the vision for this is that we should be able to collect disparate data sets, but also be able to share these data sets in an environment where especially, for example, if there's a publication from a researcher's perspective, there's a publication, you can go back and check out or verify something that you read in a paper because data sets are all available centrally. Similarly, if you're a decision maker, you have a tool that allows you to go and ask questions specifically with respect to a particular network, right? So what we do is, there are different screens to this, and I'm going to quickly go through a few of them. So one is looking at performance by section, right? And so this particular, you can, this is using the LTPP data, you can go and choose a state, you can select a section, and then you can look at your IRI history for a particular section, and also the map location on where it's located, right? So you also have the design and construction history. Now, what happens is that some sections actually have a very good design and construction history, and it's very useful to understand what happened with that pavement, why the IRI changed the way it did. And there are other sections that you don't have a lot of data in there, right? Similarly, you can go and define your own network. So in this case, so basically it has map access, which you can go and do a little grid around the area that you want to study. So in this case, this is in and around San Francisco, and you find what are the sections in that area that are part within the LTPP database. And same thing, you can get an idea of, you can build your customized network. You can understand what the pavement types there were, and also start looking at within the map location where they're located. And this section, it connects back to the previous page, so you can go and do a more in-depth analysis and in-depth understanding of what the history of that section is. So the context-specific subsets, I think, this is the most useful aspect. And again, this goes back to the question of access, is that when we have these large data sets, are our decision makers capable of accessing this data and being able to use it for their decision-making purposes, right? So what we did was we spoke with agencies and asked them, well, what kind of questions do you want to ask? What are you trying to compare? What would help you make better decisions? And so this is where I mentioned that there are 17 flavors of pavements. So you have 2 different pavement types that you can select, right? And then you can select what your pavement subtype is, and so subtype is depending on what the base is. And then you can look at the LTPP region that you want to filter it by, or the LTPP study. And this goes back to the question of, well, you shouldn't be comparing sections that are across different studies. Well, so you do have the ability to filter that out and control them for which study you're looking at. And then also what the traffic loading was, what the ranges of traffic loading for high traffic loading or lower use case sections. And then also you could filter by the functional class. So do you want to look at only, we tend to focus on primarily trunk roads, but are there other kinds of sections that you're looking at too? Oops, I forgot about that. So different kinds of, it's 2 pavement types, the region, study, traffic, and functional class. And then what this does is it allows you to run, and what's going to happen is that you'll find that every once in a while you land up with a subset where there is no data, or there is very few sections. And my perspective is that this is actually a good thing, because it allows you to see that there are, depending on how you're using this data in a study, especially if you're using it to calibrate a model, you can actually point out, you can actually dig down into what specific subset of data are you using, and how many sections are there, and what exactly are those sections, right? And then what that does is once you do that selection, it spits out these very simple statistics, but fairly useful statistics in terms of how your IRI has changed over time and what the comparison is. And so again, we're doing this for IRI right now, but this system can be expanded for any of the other properties, surface properties in the database, right? So, and then it also reports the statistics, which again is very simple hypothesis testing and gives you within a 95% confidence interval what you can take away from the comparison that you just spit out. So in this case, I think you're looking at this is just, again, this is the plot that I showed you earlier. This is just the AC, the CRCP, and the GPCP, right? So now what it does is, in a previous study, what we had done was we developed emission estimator, and we'd used the MOVES platform, which is an EPA emission estimator, to calculate the use phase emissions. So, that was based on region, traffic load, and we'd taken the speed, and then essentially what we'd do is come up with that particular yearly use phase emissions based on the MOVES estimator. So, and what we'd do is based on the first year, we'd multiply it by traffic growth in successive years to look at the use phase emissions due to traffic in between 2 operations. So the extended version for that is to look at the account for network level IRI change, and then to account for traffic as well as pavement type and the type of intervention, and be able to tie that in, right? So in the original case, you could actually choose the kind of treatment, and so we've extended that, and so now you can still choose the region and your original speed, the traffic load, and then essentially that plot you're seeing out there and you can of course choose your interventions as you go, and it gives you the ability to play around with different types of interventions, is that what you're seeing out there, that little jump in the emissions over the life cycle of this particular example case, is it tells you what that jump is after that intervention due to the change in IRI, right? So there's going to be a jump because of the intervention itself, and then there is also, and so that is actually it's a sum of the jump because of the intervention, because you have emissions associated with maintenance, and from that you subtract out whatever you're going to save because you have reduced the IRI, right? So what happens is, if you look at the slopes change a little bit after that. So what it does is it essentially does an integrated use phase emission estimation. Okay. So yeah, so I'd like to, much of this work was funded by NAPA, and even though the work was funded by NAPA, we worked primarily with public data sources, and the software is available freely. And we're hoping, we've been working with the Minnesota data set, and we've gotten a bunch of results on that. We can't quite publish them yet because we have to. Thank you.
Questions? I'll pick on something. Mustafa, sure. What's your question? Supposedly work on something.
In your last slide, I was wondering how do you consider speed and IRI together?
We're still using moves. So moves is still taking account for the speed.
But how about IRI?
Yes, IRI. So let's go back here. The IRI. So this plot, right? So that equation right up there, the IRI as a function of time over the integral, right? So that is based on, if you think back to, let me just use black, so it's going to be easier than true. Right. So the first part of that fraction, right? Let's go one more slide back. Right. The first part of this, the rate of change of fuel consumption with respect to IRI, right? That is dependent on this table, right? So in this table you get like 3 different speeds, right? 56 kilometers per hour, 88, and 35, 55, and 70 miles per hour, right? So that equation that we have out there is based on the 70 miles per hour numbers. So those are the 3 speeds that we use. So 70, 55, and I think the software is right now just doing 70 and 55.
Okay. So speed is not input for yourself.
Speed is a choice. It's not an input. So you get to choose between 70 and 55. Okay. And so then in this case, so what I've shown out, this is the equation that follows from the 70 mile per hour part of that table. But you could come up with a similar equation for the 55 mile per hour as well.
So because right now what we are doing is we're combining speed and IRI together. So
right.
We have developed an equation that works with both together. So you don't
right. So but you're are you still using this, or are you doing that independently?
We're using moves, and also just strategies work together.
Yeah. So then the speed IRI relationship should be the same then. If you're using this or
so Chatty use only 3 speed as you mentioned on the table.
Right.
But moves can consider different
more
speeds. So
correct.
like combining those two and developing some. There's some also related to that the VSP model with the specific power model, and related to that IRI. We generated and set up equations, and which is related. It's like absolutely the trend is the same.
Yeah. So it should be a more detailed version of this equation. Correct. Yeah. And so strictly speaking, we should be able to take that and stick that in here as well, as a change in the underlying relationship.
Yeah. Other questions? Very quiet today. I don't know.
Well, I wasn't very sure about how to put this talk together, because I was like, the other thing that that's come up in conversation this morning was that as we do more of this context-specific stuff, is that the whole PPT process is another attempt at doing a lot more context-specific stuff because it's a way of reducing uncertainty in our estimates.
Yeah, speaking of uncertainty, have you ever considered to include your uncertainty stuff in this IRI prediction models too?
Yeah. So when you look at the output that comes out, you get uncertainty ranges on all the values. So so in this case, right, we provide you with uncertainty ranges on pretty much all different values. The text is a little small. So yeah, it comes in with the ranges of variations. So it's not just one number. The problem when you're working with decision makers is that we don't really, when it comes to making a decision, how we deal with uncertainty, even when uncertainty is provided, is tricky. So, but we do provide that. Yes. And our the work with the Minnesota data, we've gotten some very interesting distributions. That and actually, if you go back to the paper actually goes more into depth on what those specific individual distributions are. I can show it to you if you want afterwards. But we don't talk about those in our presentation.
One thing I didn't pick up is what is the range for the IRI that you are using here?
So let me see. So between so most of the LPP data goes up to 3 meters per kilometer. Okay. So 1 meter per kilometer is roughly about 60, 65, 66, 63 right there, inches per mile. So that's the range. So beyond that, I think there are very few set of pavements that are higher than 3. At 3, you're at a pretty, and it's pretty rough pavement.
You know, it depends. I mean, it can go up to 6.
Yeah, it can go up to 6.
That's where it can be challenging because at that time, the emission will drop significantly, that will increase significantly, and it's not a linear relationship.
Right.
So, I mean, if there is something beyond your databases, are you having a model to protect it? Why?
No. So strictly speaking, since this is an empirical model, essentially it's going to reflect whatever's in the data. So you're right. So like I think at TRD last year, the folks at MIT they presented a paper where they're trying to do similar stuff, but they're doing it using their deflection model, and they're also using chat stuff. And they showed they're looking at they're using the waviness number of the pavement, and they showed their models going up to 5. But I mean,
I saw the paper.
You probably saw the paper, yeah. They showed their models going up to 5, and I didn't. What I wanted to ask was like, but how often are you seeing that? Are you seeing IRIs out there? Typically, the LGBTQ sections go on to 3, late 3s maybe, even that's rare. So at that point, I don't know if, I mean, yeah, since it's an empirical model, it might show nonlinearities in there. It'll still capture nonlinearities, but that'll affect your decision.
I mean, were you capturing the nonlinearity here?
The linear models were actually a good fit. The linear models were generally a good fit, and that goes back to we felt good about that because if you go back to the MPDG studies, the data set that was used, it showed similar linear models generally a good fit, which was actually a relief.
Right.
Yeah.
In your area analysis, data analysis, did you see any trend in pavement? You said it's based on pavement type, right? How about the pavement structure itself? Did you see any change in structure, like thickness or?
No, we wanted to look at that, but we did not. We did not say that because the data is questionable. Well, the data, if you look at this goes back to this section right here. Let's see. This data, right? The design construction history, and it's very spotty. Now, if we, I mean, again, so part of this effort also is to actually have people, like if you have data, please provide. I've had this discussion with Dr. Al-Qaidi, with Illinois Toys. If you have data, I think there is a case for warehousing because then it allows us to ask exactly these questions.
Yeah, I had a question about the application of this. So at the end, you talked about the building and LCA. So is that for users to be able to look at historical
Yeah,
cases or
yeah.
predict or look at returns?
So you should be able to do. So if you have your own data, you should be able to use it as a way of analyzing historic cases. But also, you can start off with the. So you can actually build your own. Let's see. Too many of these. So you can build your own treatment schedule basically, and play with alternative treatments. So you should be able to play with alternative treatments. And what it does, in that case, what you're getting is an estimate.
Any other comments, questions? Thank you so much. We really appreciate it.
Well, I